I've put together introductions and demos for 11 topics to prioritize learning if you're studying to become an ML engineer. In today's video, we're talking about the final 4 topics: parallel computing, REST APIs, Kubernetes and Airflow, and unit and integration testing for ML applications. I've covered the other 7 topics in the first 2 videos in this series, and you can find links to those in the description or at the end of this video. By the way, if you want to learn more full-stack data science, you can check out the content that I'm creating on Patreon and help support the channel. You can also sign up for my email newsletter, which is once a week when I upload a new video. Let's get into the demos. The first one is on parallel computing. Parallel computing refers to running tasks simultaneously on different processors. I've put together a basic example of parallel computing with Python. We're using the multiprocessing library, which is standard with Python, and I'm creating a pool of processes. And then I'm creating a big list of random numbers, and this is going to be 10 million numbers. And then I'm mapping those numbers onto a function, which is compute the square. And that's defined right above here. And what it's going to do is split that calculation up among my pool of connections. And I'll record how long this takes. So first I want to run this where I set the number of cores just to be 1, and we're going to see how long that takes. So I'm going to open up a new pane, and I want to see htop so that we can monitor these processes. / Python, and I can see all of my Python processes. Filter on the ones that are only 3.12. Python 3.12 demo. A few processes have been spawned. The first one is using a lot of CPU. Now the second one is using a lot of CPU. Using 1 core, we were able to compute this in 20 seconds. Now I'm going to try this again, but I'm going to set this to 8, and let's see how it looks different. So same code, but now 8 cores, and you can see a bunch more processes. They're all using a lot of CPU, so we're properly distributing our task. And we're going to look for this to run faster than 20 seconds now. So it only took 15 seconds. This might not have been the speed up you were expecting. Let's try increasing our array size and see if we can get a bigger difference in compute time here. I'm just going to increase it by a factor of 3. And I'm going to set this back to 1, and now I expect this to take a minute. I think what might be happening here is one of these processes is the kind of base Python process that's spawned when I start to run this script. And then the other process down here that has a lot of CPU usage is the one that's created by this pool. It's this 1 core pool that it's distributing the task to. These processes have to be communicating with each other. Using multiprocessing in this way is just introducing a lot of inefficiency. It took 70 seconds. Now let's set this back to 8 cores and use my whole system and run this again. So let's do the math on this. 20 over 15, I had about a 30% speed up the first time. And now when it's 30 million rows, my improvement is 50%. So we're seeing the benefits of multiprocessing getting better as the data is growing in size. The last thing I want to do is see how fast this runs if we don't use multiprocessing. This array that we're creating actually isn't all that big. It's only 30 million. Shouldn't really take that long. Multiprocessing is creating a lot of overhead that's actually slowing everything down a lot. So let's strip this out and I'll show you what I'm talking about. If I instead just calculate my results by computing the square of my number for num in numbers like this, and instead of distributing across multi-processes and having to worry about tracking those and Python doing that work, we're just going to call this directly in one process. And I'll prove that that's happening when we look at htop as we run this. And I'm going to just get rid of this part of the message, and let's see how quick this runs. So here's my process, 100 CPU, and it's done. It only took 3 seconds. I'll do that again in case you missed it. Again, here's my task, and it's done. So now let's show an example of multiprocessing for machine learning. Let's walk through this demo. I'm loading the iris dataset. This is going to be a classification dataset where we're trying to determine what type of flower it is depending on its characteristics, like its measurements. And what we're doing then is we're inflating that data because it's a pretty small data set. We're doing some train test splits, random forest classifier. This is going to train a bunch of decision trees, setting njobs parameter to -1. And this tells Scikit-learn to parallelize our training on all of our CPUs. And that'll happen down here when we fit the model. and then we're recording how long that took. Next, we're also making predictions, and we're going to print the training time and the accuracy. In the same script, we're going to create a serialized random forest classifier. In other words, this just has one job, so it only works on one CPU, and I'm doing the same thing. I'm going to copy all of this code here, and we're going to put this into a new file. I'm going to call it treedemo.py. So now let's run this. I need to use a Python that has Scikit-learn installed, and for me I have this virtual env folder, and inside of here I have something called nb adhoc py12, and that is a Python virtual environment that has Scikit-learn installed, and so I can run my tree demo there. So before I kick that off, let's just make sure we're all prepped with htop. And so I'm filtering on Python. Before I was filtering on 3.12, but I don't know what version I have here. So I'm just going to filter on Python, and let's see our processes kick off. So that's started, and we're training our distributed tree. And look, all of my processors just maxed out. So that's done. It took 4 seconds, and it had perfect accuracy on our data set, which, as I've mentioned before, is not necessarily a good thing. In fact, it means we're overfitting our data. But now we saw the single processor job finished, and it took 4 times as long. So if you're training a random forest, you should take advantage of this n jobs parameter. Now let's go into REST APIs, a completely different topic. And we're going to show an example of making a GET request. I'll just open up Python, and we're going to import requests. Requests is non-standard with the Python library, but it's got to be one of the most installed packages. It's the go-to library for making web requests. Now I'm going to define a URL, and this is an API that DigitalOcean has in order to check the status of their service. So if I open this up in my web browser, I can see the result, this JSON text. So let's make this request with Python. I can use requests like this, and I can get the URL as this response. I could look at the response status code, which is already being written for me as 200, but I could say explicitly verify that if I wanted to, and then I can get the JSON content from that response. I could also just look at the content directly. So I could take these bytes and I could decode them as UTF-8 string. Now what I could do is import JSON, and I could take this result here and I could load it as a JSON object by saying json.load string. This is like my data, and I can work with that data. What I might want to do is say data page. Actually, I'd want to say data status indicator. And so this is how I could check, for example, that all systems are operational. Next, let's create a REST API, and I'm going to use FastAPI for that. I have a file called demo, and let's look at how this works. It's incredibly simple. Import FastAPI class from the FastAPI library, and this is going to be a dependency for Python that I'll have to install. Another dependency is Pydantic, and we're using Pydantic in order to define what our request data should look like. Rather, what our post request data should look like. So this app is going to be implementing a get request function and a post request function. And the post request is going to take in data. This is important in the context of machine learning because when we call, say, a model that is containerized and available through an API such as this one, we might want to pass data into that. For example, train this model ID or train the model on this data path. So now in Vim, I'm going to split pane and go to my README here. And what we want to do is run this using FastAPI dev demo.py. In order to run this, I had to pip install FastAPI like this. Pip install FastAPI. And this is a system-wide installation, so Python doesn't like that and it complains about that. In order to force this to install, I say break system packages. And then I have this available to me. I'm not in the right folder. Now I can run that server. So I'll show you that. It's running a server right here, and it's showing me nothing is found here. And this is FastAPI returning this JSON for us because it knows that there's nothing at this endpoint. Now I did implement a version endpoint. So if I go there, it's printing my version. And we can see why it's doing that. If I look in the top right corner, this is the version endpoint that I'm calling. So next, what we want to do is call this with Python. Import requests.get, paste in this URL right here. calling on my local host at port 8000 and the version endpoint. And if I do this, and let's just look at that, so it's a 200 response, I'm going to call it again and get the text, and you can see the text right here. I could call it and get the JSON, and then I could take this and map it into a data object, and now my data has the version. Another way we can call this is using curl. So if I'm just in my command line like this, I can say curl and the URL, and you'll notice here instead of 127.0.0.1, I'm just calling it localhost. It's important to use the port 8000 in this case because that's where FastAPI is running. So now I want to make a post request and I want to use this add endpoint. And you can see that in FastAPI it's taking in an item, and the item is going to have an X and a Y. So what this means is I need to make a post request with data that has an X and a Y field. So I'll say curl-x post, define my data X field, and I need a Y field. So I need to define a header for my content type, and I need to make sure that I'm telling it I'm going to send you JSON data. Then I'll just say my endpoint, which was HTTP localhost 8000, and then the endpoint was add. And here we go, it's doing that addition. So what I could do here is I could pipe that result into a file result.json, and then I could open up that file and notice that this is just a JSON file here with my data. And that's all I want to show you for REST APIs. Now let's talk about Kubernetes. In this demo, I'm going to run a local version of Kubernetes called Minikube. Kubernetes is a distributed way of running applications, and what it does is manages stuff like auto scaling up depending on your workload. But this Minikube is designed to test Kubernetes applications on your computer, and it works with Docker. So we're going to learn specifically right now about Minikube, but this is going to give us hands-on experience that's really similar to using real Kubernetes. We're going to run a FastAPI application on Kubernetes. A real-world use case of this is that I have a machine learning model that makes predictions. So I'm going to containerize that predict method in a FastAPI REST API application, and then I'm going to host that on a Kubernetes cluster so that if I'm getting hit with a lot of requests to make predictions with my ML application, Kubernetes can scale up and handle that. So let's look at my FastAPI app. Here I have a Docker file. Here I have this Uvicorn dependency. That's something we didn't see before. That's used to run FastAPI as a production application, and we're running it on port 80 of the host inside of Docker. This is what my app looks like, and it's identical to what we were just talking about. It just has this version method and an add post method. And now let's talk about the Kubernetes stuff. So I've got this deployment YAML, and this is going to define my Kubernetes deployment. And specifically look at this line here. I have 3 replicas. It also has some specs specific to the fact that we're looking for a container with a certain name. And I've set this image pull policy to never. In production, we're going to want to pull our images from like a remote somewhere. But in this case, we're just testing locally. So I'm going to be telling Kubernetes, just look for what's running on my local system. Next, I have my service, and this is going to reference my FastAPI application. So for now, let's not worry about this Kubernetes stuff and just have a look at this Docker file. And I'm just going to build and run this Docker app to make sure it works. So here it's pip installing my dependencies, FastAPI. That's done, and now I can go ahead and run that. And let's open up Docker Desktop and see what's going on. So I've got my image, and it has a running container, and it's also showing me the port mapping from port 80 inside of the container where I have a production instance of my API running to my computer here. So if I type version, I can see the version endpoint is working. Okay, that's great. So let's stop this. Clean things up. I'm just going to get rid of my image. First, we need to install Minikube, and I did that using these 2 commands. This is pretty interesting in and of itself because all I'm doing is grabbing this binary file from this endpoint. Right here is just a file being hosted on that server, and I just pull this file onto my computer. After I run that, I've got the file just sitting here, and what I do is I run this install command, which moves this file into this directory. And since local bin is in my path, then now minikube becomes available as a command on my computer. This also sets the proper permissions. Instead of sudo install, you could just say sudo copy, or even just move it. But after that, you'd also need to set the permissions. So you'd say something like this: chmod plus x. This line here is analogous to these two lines like this. But in any case, once you've installed minikube, we're going to start our cluster up. So I'm going to run minikube start. You can see here it's creating a Docker container, and it looks like it's ready. So if I go back over to Docker, I can see that here's my images, and I've pulled this image, and I've got a container running called minikube. Let's open up the minikube dashboard. So there's nothing really going on, but once I deploy my app, we're going to see things appear here. I'll go down to my services, and I can see this Kubernetes service right here. Next, what I want to do is apply these Kubernetes manifests. So I'm going to apply my deployment one, and then I'm going to apply my service one. And after I've done this, let's see if things look different in our Kubernetes dashboard. So now when I look at workloads, I can see that I have one deployment and I've got 3 pods. Right now they've all failed, and that's because I haven't built this container. So we want to see these go green. At this point, what we're going to do is configure our shell environment so that the Docker CLI communicates with the Docker daemon inside of the minikube virtual machine instead of the one on the host machine. And what this means is that when we build our FastAPI app, it's not going to show up here as a container. It's going to be running inside of this minikube container. If you're confused about this, it's just because I'm not explaining it well enough. But let me show you at least how we do it. If I run minikube docker env, it's going to give me variables that I can set for my environment so that it points Docker in the right place. Run this inside of an eval command. I'll just go ahead and evaluate all these things. So for example, this minikube active dockerd, if I was to print the value of that, we're going to see the value has been set. Now I'm just going to go ahead and build this FastAPI, which is not available here. It's here because I need to be in the same folder as where my Docker file lives. So it's building this and it's reinstalling everything from pip. And now if I go down to my images, I'm not actually going to expect to see it. I might see the image, I don't really know. Yeah, so I don't even see the image because it's kind of being managed inside of this minikube environment somehow. Let's look at some information. If I look at my services, I can see this FastAPI service. I can look at my pods. And we can also see these things in our app. And here we go. So in my dashboard, now things are green. And our FastAPI deployment looks like it's going to be working. I've got these 3 pods. So when I run a task in minikube, it's going to send that task to one of these 3 pods. So what I'm going to do is set up some environment variables for these. And I'm going to name these environment variables the pod names. Service 2, and here's service 3. So lastly, I need to know what my app URI is. And I can run this. So I'm going to say minikube service FastAPI service. And that's going to launch this as a service. And you can see the URL up here. So I'll open up yet another tab. And unfortunately, I need to make sure my environment's set up. So I'm going to redefine all of these services. And actually, let's reconfigure things a little bit. I'm not really liking any of these configurations. I'm going to get out of here and we're going to look at it up here. Open this up a little bit. Got to get these services right. Great. And now I want to define my app URI, and that was just going to be what we were looking at right here. Finally set up to test this. Let's look at the logs from the first service, the second service, third service. And now we're going to make our request. So I'm just going to make this version request, and this is not working. Okay, so that's just because I defined my app URI with a trailing slash, which I didn't mean to do. So let's try this again. So here we see version 0.1, and this is the response we expect. So now let's look at these logs. I want to look at the logs from service 1. I cannot see any requests come through. So let's look at the logs from service 2. Here I don't see any requests coming through either. So that means I expect to see logs at service 3. And here it is, 200, okay. So that request was sent to service 3. Let's run it again. In fact, I'm going to run it a few more times. Here's my service 1 logs. We can see that 2 of those requests were sent this way. Here's my service 2 logs. It still hasn't got any request. And service 3 got the other one. Next, I can try this with a post request as well. So this is the same type of post request I made before. And I could go and make another one. This result is around 30. And if I now look at my logs one more time, we're going to see that service 1 didn't get any of those. Service 2 got 2 of those post requests. And you can see it's calling the add endpoint with a post request here. And so service 3 didn't get any of them. And that's all I want to show you for Kubernetes. So let's tear all this down. I'm going to say minikube stop. And I'll run minikube delete all purge. Now if I go back over to Docker, I can see that there's no containers running, and I could clean up this image if I wanted to. And I don't need to worry about my Docker environment, because as soon as I open up a new terminal window, those environment variables will be cleared and my Docker commands will be running like normal.
Attention, brave data scientists! The kingdom is in peril, and only you can save it. Join us on an epic quest to get a forecasting app into production, from the realm of higher thinking to the land of Jupyter notebooks and data exploration, through the kingdom of NeoVim and implementation, and finally to the castle of production APIs and Streamlit. Embark on this journey and equip yourself with the skills to train and productionize a demand forecasting model. The kingdom awaits. Are you ready to become the hero we need?
Next, let's talk about Airflow. Airflow is a tool for job orchestration. So say you had a batch job that every day had to run. Airflow would be a tool to manage that job. You could use it to schedule the job. You can look at the logs of that job and make sure it ran correctly every day. And it also does things like automatically retrying your jobs if they fail. You can write DAGs with Airflow so that your jobs can have multiple tasks that depend on each other. You can also do things like update a specific data set, and Airflow has this concept of a data set. So when that job has run and the data set's been updated, then another job can be triggered. So for example, maybe we have a DAG that updates a training data set, and then there's another DAG which says whenever that training data set is available, let's retrain our machine learning model. You're going to see just how easy it is to get Airflow up and running on our local computers using our favorite tool, Docker. I have a Docker compose file sitting right here. I'm going to go ahead and remove that because we're going to pull that right now using this curl command. I was talking about curl earlier, and this command LFO, it means take this file here, follow redirects, and then put the file Docker compose YAML as the same name on our local computer. That's what that O flag means. So if I go ahead and open this up, this is the Docker compose file that's going to run Airflow for us. It's pretty gnarly and there's like a lot going on in here. Let's pay attention to this part right here. We have some volumes, and this takes from our local computer these Airflow project directories, and it's going to map those into our container in this opt airflow dags folder. And these are actually going to be created for us. Now, I've already created dags because I have one demo dag that we want to look at, and it's called ZC demo. And I'm importing Airflow and then some operators. I have a Python operator and a branch Python operator and a bash operator. And what this does is I wanted to have an interesting looking DAG, and that's why I'm using this branch operator. But this Python operator is a really common one we'll use. So let's just look at that right here. We have a task ID. These have to be unique. Each DAG, each task ID needs to have a unique name. And then I have a Python callable. So this is just going to point to a function inside of this file, or it could be a function that we import from another file. But as long as it's available in the runtime of this file, we can call it. And we're just calling training model in this case, which just prints something. And just so that you understand, when we run this, it's returning a random integer between 1 and 10. And depending on the result of that random integer, we're going to choose a path for our DAG to run. And that's how this DAG is structured. The other important part is right at the bottom here, we have our order of operations. So whereas we're just defining different tasks, this line here is what connects all those tasks. When I write these, I typically use indentation. Lastly, I got to ignore this. So this is what's going on here. We have this training model tasks, and then a downstream task is choose best model, and then the downstream task is accurate, which again is this name right here is the sort of Python identifier, but this task ID is what Airflow uses to name these tasks. I think you have enough context to understand when we start looking at this. Now, the first thing we need to do is initialize the database. I'm going to make sure I'm in the right place here. What we're going to say is docker compose up airflow init. And this is looking in Docker Compose, and it's just grabbing the Airflow init service from there and running that. All right, so that's done running, and let's go over to Docker. We pulled images for Redis, Postgres, and Airflow. Redis, I'm sure, is used for caching in the application, and Postgres is used as the Airflow database. I look at my containers, I have a stack of services running, and even though the Airflow init task has exited, my Postgres and my Redis containers are actually running right now. So now let's bring up all of the services. I'm going to say docker compose up. And this looks at all of the services in the Docker Compose file and launches all of them. If I go back to Docker Desktop, now I've got a bunch of services booting up here, including an Airflow worker, a web server, and a scheduler. The worker is the node where the tasks are actually going to run on. So the scheduler task will send it to a worker to run. And in a production deployment, you'll want to have multiple workers running your tasks. So when things are running at the same time, they can run in parallel. Let's load our Airflow web server. It's going to be available at the default port of 8080. So I'll log in as user Airflow with the password Airflow. I can see all of the example DAGs, but I want to look at my demo DAG, which is ZC demo here. So you can see that it's scheduled to run daily, but it's not on yet. So as soon as I turn it on, Airflow is going to trigger that to run now because it hasn't run yet today. Just refresh the page and we can see it's already ran. So let's run it again so we can keep an eye on it this time. So now these tasks are queued. They haven't run yet, and now they've all run, and now the downstream task gets triggered. Let's see what the graph looks like for this. So if I look at, say, this one, we have 3 upstream tasks. These are our initial tasks, and then this choose best model depends on all 3 of these being completed. So if I go over to my DAG, we can see how that's working. I have these training model tasks, which is a group of 3 tasks for model ID A, B, and C. And then if I go down, I can see that choose best model depends on these. So this will get run after all of these 3 tasks are completed. After choose best model, we have 2 downstream tasks. And in this case, the way it works is we're only sending one of these tasks to actually get run, and the other is going to get skipped. And that's why it's pink here. It's being set to be skipped. Inside of these, for example, training model C, I could look at the logs, and I can see it's returning this info, which is just C, and then a value of 1. And why is it doing that? Well, if I go back up to my task that I'm calling, this Python callable, here I'm printing the model, which is C for the C model, and then it's returning a random integer, right? So if I go to model A, I can see it's printing A, and then it's returning a value of 7. So let's say we had a situation where model B for some reason failed. What that would look like is this would be showing me a red dot for failed. And then the downstream tasks would also have failed. They would not have run in that case. If B fails, all of the downstream stuff is going to have failed. So I can manually set these to failed to sort of pretend that that's what happened. C would have ran, A would have ran, and then B has failed, which means all the downstream stuff failed. So in a case like this, what I would do is I would go to B, and I could look at the logs, and then I could say clear task, and I'm going to clear all of the downstream tasks. And this is the default configuration when I click clear tasks. I could say like only the upstream tasks or all of the tasks, but all I want to do is clear the downstream. I'm just demoing this because this is something I'll typically do with Airflow. Now when I run this, look, all of these have been cleared, and so this gets rerun, and the downstream stuff gets rerun as well. So now my graph is showing all green except for this skipped one. And if I look at the logs for this B, I now have 2 sets of logs. In the first log, I returned 1. In the second, I returned 4, just indicating that these are separate logs. Next, if I go back to my DAGs, I'm just going to click on the active ones, which is just this one that I've turned on. I can see some recent tasks, like all these successes, some of these skip tasks, and I'll see failed tasks showing up here if things have failed. And lastly, let's talk about the schedule. It says at daily. This means every day at midnight. But what I would typically do is use a cron ID for this instead. So what I could do is say, run this on the 10th minute, 5th hour, every single day. So if I update it like this and refresh, I'll see the schedule update as well. And actually that's caused it to trigger off another job. That's not the case in general. For example, if I don't know, go back to the 2nd hour and refresh this, it probably won't trigger off another job, although it's been updated here. You could also run things more than once a day. For example, if I did it like this, it would run on the 10th minute of every single hour. So lastly, if I turn this off, it will no longer run on this schedule as it's been paused. So that's the very basics of Airflow, and now let's just tear this all down. I'm just going to stop all of my Docker containers here, and if I really want to clean everything up, I could go back into my Docker desktop application, and I could go to my containers and just delete them. Even though they're stopped, they're still around, and then I could go ahead and delete my images as well. And lastly, there'll be volumes that have been created, like my Postgres database, which stores all my Docker run information from the previous runs, and I could go ahead and delete that. Now we're totally cleaned up and ready to move on. And the last topic I want to talk about is unit testing. In order to demonstrate unit testing, I created an entire ML sample app. It's in this app folder here, and I have a library called ML app, and it does data prep, feature engineering, and machine learning. And then I have a models folder, which is going to store our model artifacts or pickle files, binary files of our models. I have a predictions folder, which is going to store some results. And then I have a tests folder. And these are the tests we're going to talk about in this part of the video. Now, before I talk about my tests, I should describe how this application works. And the best way to do that is to look at my train model function and my predict function. As we can see in our README file, train model works in this way. We define a path to our training data, and we label a model ID. And the predict works really similarly. We define a path to the prediction data, the data that we want to create labels for, and then we also define the model ID. Now in the first case, we're creating a model ID, and it could be anything, and we're going to save the model with that ID in the file name. And then in the second command, we have to use a model ID that we've already created in order to predict something. And actually, I should show you what the data set looks like. If you're following along with me, this data set should be available inside of the Git repository. However, you could also go to Kaggle and download it from here. It's a video game sales data that we've talked about earlier in this series, back in the first video, and it has a bunch of different video games with information like when it was created and rating information. And what we're going to try and do here is see if we can predict the sales given the ratings that critics have given the game. And let's look at how we're doing that. Here's our train model function. I'm importing from my ML app, this is my own source code for the machine learning model, various functions. And then we're calling those functions. First, I'm going to load the data, then we're going to filter that data, and then I'm going to do some feature engineering. And then lastly, we are running the train method. And inside of this train function, we're going to be saving a trained model. So if I go to the definition of this, I can look at how we're doing that. I'm calling a hist gradient boosting regressor, and then I'm printing some training metrics. And lastly, I'm storing the model right here, and I'm storing it at this model path, and I'm just indicating where I stored it in a log. And let's look at how we do the predict. This looks very similar because I still need to load data and filter it and create my features, but now I'm just calling a predict method instead of calling the train method. So if I go to that definition, we can see how the prediction is working. And here I'm first loading a model, and this is going to return that hist gradient boosting regressor. But now, instead of needing to train this or something, I'm loading it from a pre-trained model, something I've saved on my system. And then I'm storing a prediction result to the place on my computer, which I mentioned earlier was going to be this predictions folder right here. Now that you have a general idea of the application and how it works, we're going to talk specifically about the tests. And first, we're going to talk about unit testing. Unit testing is concerned with testing the functions of the application directly. And I have a tests folder, which it's important to put an init file in here so that Python recognizes this as a library folder. And that way I can do things like this: import from local libraries. In this case, I'm importing from MLApp, and here I'm importing from config. So if I go into MLApp, and then I have this config file, and this is specifying some config. So for example, my target column and my features column, and I'm bringing some of that information in here. First thing I'm doing is testing the loading of the data. So I want to test the prep load function, which is here. If I go to the definition of that, this is in my prep load file, which happens to be in this data prep folder. And all this function does is load some data and return it. So I do that here in my test, and then I'm just asserting that it has the correct length, which I'm setting up here with a global variable. I'm also setting the train data file as a global variable. Next in this file, I want to test all of my data prep functions. So over in my tree, if I say prep filter here, I have a different function which takes in a data set and it filters that data down. First, I load my local data, but notice how I'm not using the prep load function anymore because I want to test these functions in isolation. For example, it might be tempting to do this and then not load the data that way, but load it in this way. But that would be more like an integration test because then we're seeing how prep load works with prep filter integrated. I don't want to do that, right? I want to test this in isolation, just this function. So that's why I'm calling read CSV here. Then I'm asserting that this target column's in the data and that the other columns, like there are columns in the data that I expect. So next we do some feature engineering. And down here is where I test the feature engineering. I have a function called test feat bin. I'm reading the data in again, and then I'm calling this feat bin function. And now I'm just iterating over the results, and I'm checking that things are working as expected. And without going to the details of this function, the important part to pay attention to is this assert statement. After I've basically done a calculation to check how my feature engineering has worked, I'm just going to assert that we're seeing the data in the correct way. I'm asserting that the feature engineering has been done properly. The last unit test folder I have set up is to test the ML application directly, and this tests functions in this ML folder. So in here I have a predict and I have a train file, and each of those have different functions inside of it. So I have this kind of publicly accessible function train, and then I have some more private functions. Now there's nothing stopping us from calling these private functions outside of here, but the underscore just kind of indicates that that's not really what they're meant for. They're meant to be used internally, and they're called by this train function. So let's go back to my test ML and see how I'm doing this. In order to test the training of the data, I have gone ahead and imported one of those private functions right here, and I'm calling that directly. And notice how I'm just reading data. I'm not doing the feature engineering or the filtering. I'm actually just reading a data which I've specifically prepared for this test. So I'm calling it PyTest ML train. This is data that's already been put through feature processing and is like ready to go. And this again goes back to the point of not doing an integration test by accident. I want to make sure I'm doing a unit test. I only want to test this train function. And in this case, how I'm actually testing it is I'm trying to call predict on the resulting model, and I can tell if it's not been fitted or not by checking for this not fitted error. And that's something I'm importing from Scikit-learn. Of course, you might want to test your model training in a more comprehensive way than just this. Next, I'm also testing that we can get training metrics. Here, I'm loading a model that's already been trained, and then I'm loading some data that we want to make predictions for. I'm getting those predictions using this get training metrics functions, and then I'm asserting that it has the correct type, and I'm also going to expect that it's in a certain range. And the very last unit testing function I have is for testing the prediction. This is similar to the get training metrics function, except now what we're going to do is get the actual result of the model, not just the error, but the result on some sample data set, and then I'm going to make some assertions about that, like the length of the predictions is what we expect, and their type is correct, and also that these predicted values are within the expected range as well. The other type of test is an integration test. I'm defining a training data set and a prediction data set, and then I'm defining a model ID. And this model ID is going to be something that we're creating right now during the integration test. So this could be a new ID. I might just go ahead and change it right now. That would be fine. And let's start here with the model output file. So when I'm testing the training integration, what I do is I make sure that there's no output file that exists yet. If it does exist, I unlink it, so I delete it. That way we're starting from a clean slate. I define my random seed, and then I load my data using the prep load function. I filter my data, I create my features, and then I train it. And this looks really similar to what we're doing in train model right here. I've just copy and pasted this code. Lastly, what I'm doing to assert that my test is successful is I'm checking that the output model file does exist. You'd probably want to do more comprehensive assertions than just this. Now for my predict method, I'm doing something similar. I'm starting with the prediction output file that I want to check for at the end of this test. And if I find it, I'm just deleting it. Then I'm running through the same types of functions that I called when I ran predict.py over here. Again, I just copy and pasted these guys. And now what I'm doing is I'm asserting that this output file exists after calling the predict method. Then I'm doing a few more things. I'm loading in the actual prediction result, and I'm checking on that to make sure it has the right length, and to make sure my target column, the actual prediction itself, is in the result, and some other assertions about the other columns that I expect to be in this result. So let's go ahead and run these tests. I'm going to go into my app. If I look at my requirements, I can see that I have PyTest as a dependency. If I go into Python inside of my virtual environment and I say -m, now I have access to PyTest, which is installed in that virtual environment. And I'm just going to run that right like this. You'll see it's collected 8 items to test, and now it's running all of those tests. I could run that again with the V flag for verbose. It'll give me a bit more information about each test that it's running and if it passed or not. And lastly, since I didn't clean up any of the results of that test, I could go into my models folder and I can see that there is a model created, and then I can look at the predictions. If I open up my JSON model, I can see some of the revenue predictions which are being made for certain games. And I can also open up my CSV file and I can see the same result in a CSV format, and these are the results of my model. So that completes my ML engineering starter kit. I hope you found these hands-on demonstrations valuable in addition to a high-level overview of the ML engineering landscape, actually getting in there and using the tools and seeing how things work on your computer, I think is really beneficial in addition to just learning about the concepts. If you like this video and this series, I would appreciate it if you gave me a thumbs up and consider subscribing in order to support the channel. Namaste.